looking at space curves, vector functions. So let's get right into these guys, get them done. There are four main types of questions that we're going to cover in section 13.1. How do you find the domain of a vector or space curve? How do you find the limits of them? How do you do graphing, which is fun, and we've kind of covered that, and how you do intersections in 3D. What do space curves look like when they bump into other shapes, surfaces, and whatever? Now let's start with the first one. How do you find the domain? So here's a space curve. When you talk about the domain of any space curve, you're really talking about the usable values of t. So it's going to be a single interval. It's not going to be a three-dimensional region. It's just going to be t between here and here kind of thing, right? And the way that you tackle it is you take each component, right? Would you agree that t squared plus 1 has no problem? So basically everybody, right? Minus infinity to plus infinity could be used. Now, if I pick on the middle one, would you agree that there's a problem with one value of t, but only one value of t? Would you agree t equals 0? Right, so don't use 0. Okay. Now, if I was just combining these two, then the domain would be from negative infinity to 0, and then from 0 to infinity. Would you agree that's in interval notation? That's how you would say you can't use 0. Bit clunky, but that's what it would be. Now, what about that guy? What values of t can you use? And we'll talk about the ones you can use in that expression.
Greater than or
Anything
equal to
greater
3.
or equal to 3.
That's what I heard in 2 places. Now, what you have to do, and it does get messy, and there's kind of no way of avoiding this, is you have to combine all 3 together. In other words, find values of t that will work no matter which equation you used. So right now, if I was saying it in English, you can use any number you like, as long as it's not 0 and it's bigger than 3, okay? So you put that together, isn't that basically just numbers bigger than 3? Does that make sense? Because if you're bigger than 3, won't you not be 0, right? And it works. Right, let's pick one of theirs. This is their question 1 then. The space curve that they're talking about has got a log in it with t plus 4. It has a t over a weird square root. And it's got a 2 to the t. Okay, so I'll start with this one. Do you know that logs are no good with negative numbers, right? You can't find a log of 0 and you can't find a log of negative numbers. So I need this fella to be greater than 0, which means I need t to be greater than negative 4. So I'll put a little bubble around that to remind myself. Now the second expression looks like that. The only problem you're going to get with this expression is if the bottom thing, right, the thing inside the square root is negative, right, that's going to cause a problem, and you don't want it to be 0. So when you put that together, you need this to be true, great? The thing inside the square root has to be greater than 0. Do you know I'm not allowing it to be equal to 0 because something over 0 is also bad news, right? Now, if you take 81 take away t squared and you draw it like that, can you see that that really becomes numbers between -9 and 9? I would just stick it into Desmos and look at it, right? When is this positive? It's positive from here to here, right? Can you imagine? There's your t-axis and there's your y-axis. Now, you put a big circle around that guy. Now, would you agree 2 to the power of t has no problems, right? Anything will work. So I need numbers that are greater than -4, but they have to be between -9 and 9, right? So both of these have to work, right? So I have to kind of combine them. And if I did that, what would the interval look like?
Parentheses -4, 9, parentheses.
Yeah, agree? Numbers from -4 don't count me up to 9, right? Curve brackets, because you're not allowed to equal them. And that's how you find domains. Right, you take each one separately and find out what t has to be or not has to be, can't be, and then you merge them all together and you find an interval where everybody is happy with those numbers. Zoom through that maybe quicker than I should. Are we comfortable with how you find domains? Can I move on? Okay, right, let's do our second topic, which is limits. Let's find the limit as say t tends to infinity of some expression. Right, here we go. This is question 4. 7 plus t squared over 7 take away t squared. 7 times the inverse tan of t, and 7 take away e to the -2t over t. Right. First time probably everybody here has ever seen that kind of weird limit. How do you find the limit of this space curve? I don't need the details, but just the general process. How do you think you would find the limit of this?
Do each one separately.
That's all you do. So you find the limit as t tends to infinity of that guy. You find the limit as t tends to infinity of the middle guy. And you find the limit as t tends to infinity of the last guy. Kind of like this question. It's a good choice by the textbook because it uses different techniques from your past. So if I wanted to do this fella, what method could I use? What method would I use? If I actually got a choice of 2, which one would you use?
L'Hopital's.
Right, L'Hopital's works. None wrong with that. It's good to answer. Couldn't I also divide top and bottom by t squared and do it that way? Can you trust me? The answer is eventually -1, no matter which method you use. Okay, this one here is brute force. Brute force is just you plug in infinity. And no, that answer is not infinity. What is the inverse tan of infinity is actually what angle has an infinite tangent. It's a number and it's got pi in it. Does anybody know what the inverse tan of infinity is? What angle do you get an infinite tan?
Halves.
Pi over 2. Pi halves. So 7 of them gets you 7 pi halves. I don't think there's a choice with this last one. What technique will you use for that fraction?
L'Hopital.
Yeah, I can't see any other way of tackling that. So differentiate that guy, you get +2 e to the -2t over 1. If you then plug in infinity, Oh, that's interesting. Does anybody know what the answer to that is? Because it is a number.
0.
It is 0. How did you figure it out?
Because the negative infinity right there is gonna cause it to flip sides, and then it'll be 2 over infinity.
Nice way, yeah. So put the package together. The limit of that is -1, 7 pi upon 2, 0. And once you've done one of those, haven't you done every other one in the universe? Because don't you know how to do limits? And you just take each piece and off you go. I think you only get one example of it, and I've probably just used it up. But that's how you do it. Now, the next bunch of questions on graphing. And get us to play with some software. And I'm going to see if I've got my window open. And I'll move over here so I know it's there. And let's go. So you go here, little curve bracket, put in 2t, comma 1 divided by, I don't know, t squared plus 1. Okay, where's my plus? Oh, it's there. T squared plus 1, comma, and then put in, I don't know, sine t. There we go. A pretty boring curve. I should be able to make that more interesting. Okay. Let's try a cosine t. Yeah, that should make it more interesting. Ah, that is cool. Oh, look at that little guy. So can you just plug it in and look at the thing and you get some kind of nice weird curve? Yeah, okay. I'm not going. I'd spend hours on that if you left, if you left me on my own. So I'm just going to move on very quickly. But isn't there a bunch of questions? You'll find out that there's a bunch of questions in your homework where you're being asked to find what something looks like. I'll show you one of the homework questions. Right. I don't know if it's my software or that, but it looks like it's my software. Yeah. Okay, that's the guy. And you plug him in. And one of these pictures is the right one. And let's pretend it's that one. Right, you pick it. For some reason, they've disappeared on me, but trust me, there are pictures there. There was earlier on today. And so you get a little, it looks like a spiral, it looks like a hill, it looks like whatever it is, and one of them will be correct. So the questions that are involving you, I wonder if it's probably that that's bugging it up. Stop doing that. Nah, who knows? Oh, can you see what I can see now? Can you see the graphs? Okay, so yep. That's what it should look like. One of those is the one that you've got, and there it is. Oh, that is cool. And let's move on now. Can I call that done? That if they give you a graph, you can just put it in and look at the picture and then see the 4 and pick the right one that's done. So check it off our list. Now we're going to look at intersections. So the kind of questions are, where does a space curve intersect with the surface. Okay, so suppose I have a space curve. This is a version of question 10. My space curve looks like this guy. T, 0, 5t, take away t squared. That's at least the way I would write it. This is what it looks like in WebAssign. These are totally equivalent, aren't they? Like I, no J's and a K, right? I, J, K. I always write every question I get like this. Even if in the book it starts off life like that, I always do that. You know how careless I am. Isn't it just easier if you write it this way to know where the zeros go? Because if I do that, I sometimes forget, you know, who's missing or the order. Anyway, I want to find out where this space curve, right, intersects with z equals x squared plus y squared. So how do you think we do that? I think we did one with a line meeting a plane yesterday. How do you find out where this space curve intersects with that surface?
Substitute in the x's in the space curve and for the xyz's.
So the z becomes, if I pick you up right, becomes this guy. The x becomes this guy, and the y becomes that guy. Is that what you mean? Yeah. Right. So what you are going to get in these intersection questions, aren't you essentially going to have to solve some expression involving t? Right. Now, in this particular case, I think I'm going to move everything over to this side. Are you okay with that? Add a t squared, take away 5t from both sides. I don't want to make my life too hard, so I'll just pull out t as a common factor, and that gives me two solutions. So far, so good. Now, if the question had been, tell me the t values, I'd be finished. But the question is, tell me the coordinates. So I now need to know, what does that mean, right? What in 3D space, what is the coordinates when t is 0? And what is the coordinates when t is 5/2? So don't you then just return back to here? You plug in 0, and you'll get the coordinates of the first one. So let me do that. If you put t equals 0 into this space curve, you get 0, 0, 0. We call this a position vector. It's really the same thing as the coordinates. So there's your coordinate, 0, 0, 0. And then the other one is actually going to be, I suspect, at least some numbers. So 5/2 into this space curve gets me 5/2, 0, and whatever 5/2 times t is, so that's, I don't know what that is, and I'm not going to risk it. So it's going to be 5 times 2.5, take away 2.5 squared, and I get 6.25. Now what's that? 25 quarters. There we go. So this space curve meets up with this surface, and it intersects in two locations. You could go into GeoBra and actually, you know, draw the thing. That's roughly what z equals x squared plus y squared looks like if you do it right. It curves up, right, like a big parabola. And this space curve that we've got here, can you imagine that it comes in, hits it at the origin, and then pops out here, and that's the 0, 0, 0, 1, and that's the other one, right? So in this case, can you imagine a space curve could meet up with a curved surface many times? Agreed? You know, curves can curve back in themselves and, you know, poke another hole in the shape. So what we're really doing is finding out the intersection of a surface, right, which is a curved piece in 3D, meeting up with a bent piece of wire, right? Think of that as a space curve. And that's the first kind of intersections. And that's what questions 10 and 11 look like. And the other kind of intersection is oh, they get you to do pictures, that's cool. It's 13. And it asks us to find a vector function. And it represents the intersection of two surfaces. Okay. Now, the two that they're going to do, I'll write them in a minute, but I'm going to show you two other surfaces that at least I can visualize. Can you imagine one of the surfaces was a cone, right? The skin of a cone. And my second surface was a plane going like this. Can you imagine the plane like being a knife and it cuts the cone? When it cuts the cone, won't the points of intersection look like an ellipse? So the space curve that they're talking about, right, is that ellipse. Does that give you a kind of visualization of what you're looking at when you're looking at one plane intersecting with another? Can you imagine a cylinder poking a hole in a sphere? Can you imagine the kind of surfaces that would generate, right? Can you imagine a cone interacting with another cone coming in side on to it, right? You imagine one cone crashing into the other. What would the surface of it, what would the region look like? So that's kind of the visualization. Here are the two surfaces. That one's actually an elliptical cone. And this one, well, that one's do you know that guy I couldn't make happen? You know, the one that's this fella that goes all the way up. Remember that one? That's what he looks like, right? So y equals 2x squared going vertically upwards, right? So you get that fella, and it meets up with a cone. Ooh, that'd be weird. Interesting. I think it would be some kind of quadratic, not spiral, but a kind of quadratic edge thing. That's what my brain's telling me. Well, we have to figure out how on earth we're going to make that happen. Now, a space curve, the guy that we're going to be writing down, has an x component, right? A y component, and it's got a z component. And it doesn't look too obvious yet how we're going to do it. I don't know if you're going to like this technique, but it is kind of cool. You take whichever one of the two equations has two variables in it. Because if they both have three variables in it, you can't do the question. Or at least I don't know how to do it, right? But one of them will have two variables in it, right? And that's this one. And the other will almost guarantee have three, right? So you choose the equation that's got two variables in it, in this case, y equals x squared, and you make x equals t. And since y is 2 times x squared, y will now be 2 times t squared, which means this is t, and this is 2t squared, because this is x and this is y. And as long as those two are true, it's on this curve, or this surface. And all I need to do now is find out what z is. Well, once you've picked the equation that's got the two parts, pick one of them to be t, and the other one will come from it, right? Could I have said make y equals t? Sure, but wouldn't it be a much uglier answer? So making x equals t kind of makes sense here. How am I going to get the z then right? The third piece in terms of t.
Would you solve or substitute the t and the 2t squared back into the x and y squared?
And what does that get me? 7t squared plus 2t to the 4. Was that easier than you thought, but weirder than you thought? And that space curve would represent the intersection of this surface with that surface.
What about the 2? You're not squaring
Say again?
that.
Say again, David?
You're not squaring the 2?
Did I forget to square the 2, he says. And I did. Yeah, fixed. Oh, come on, that is cool, isn't it? You could spend forever in the day on this, but we have to move on. And you only get one example of that because it's not the major thing that we deal with. So we're finished. You've covered everything that you need for homework. So the stuff I'm about to do now is for next week, right? So it's not going to appear anywhere until then. You know you're not going to go far without calculus coming in, right? In particular, differentiation for sure, and very, very little integration. So I want you to imagine that this is a space curve in 3D. Right? This is my space curve. Right, so it's spiraling. How about it's a roller coaster? Can you imagine a roller coaster in 3D doing its all, up and downs and loops to loops and that, right? And let's pretend that this guy is t squared 2e to the t 5t minus 1, right? Let's suppose that's my space curve. The first thing you would like to do is, what does a derivative look like of a space curve? And they're called, not surprisingly, r dashed of t, right? The notation makes perfect sense, right? That's what you would call it. Again, for most of you, if not all of you, you have never seen a derivative of a space curve. If the world was nice and life was simple, how would you differentiate that space curve?
Power rule.
Agreed. Would you just differentiate each part separately? Is that what you're saying as well? And the good news is that's exactly what you do. Now, wait a minute. Derivatives should be numbers like 42 because derivatives mean slopes of tangent lines. Well, they do in 2D, but in 3D they don't. Right? A derivative in 3D space isn't a vector. Right? It's got 3 pieces. For instance, if I said, what is r dashed of 1? The answer would be 2, 2e, and 5, right? It'd be a 3D vector. So we have to imagine or interpret derivatives in a different way now, right? They're not the slope of a tangent line. And you might think, well, why can't we make it a slope? I want it to be a slope. I don't like new stuff, right? Right? Well, you're going to live with it. You can't have slopes in 3D space. I want you to imagine, Eli, that I've taken you up to space and I've threw you out and left you. And you're floating there in the deep space, no idea where you are. Which direction is up, Eli?
There is no up, right?
Correct. And if there's no up, How can you have a rise and a run?
Can't have one.
Can't have one. Have I convinced you then that slopes are a bad idea now for 3D? Right? Vectors are what you are dealing with. 2D is like a very, very special case, right? The generalization is different, but it does have an imagination thing. Back to my roller coaster. I want you to imagine that that there is where you would be at t equals 1, right? And this here is the vector r dashed of 1, right? That's this guy here. It is a tangent line. Can you imagine you can still have a tangent line in 3D space, right? Imagine you're traveling along this roller coaster and it's broke at that point. The vector that you shoot off to your death in is the derivative. Imagine it broke, right? You go. Wouldn't you go in a direction? Wouldn't there be a vector attached to that direction? That's the direction vector, right? That's the derivative. It's the angle or the direction the curve is pointing at that particular point in time, right? Imagine in 3D space at any given point in time, the curve is pointing somewhere. It's like the tangent line. Now, if you find the magnitude of this vector, right, you find out how big it is. That's the speed at which you shoot off the roller coaster to your death. So you might shoot off at 40 miles an hour, you might shoot off at 4 miles an hour, but you're still going to die, right? That is your vector. So your analogy here, I like that analogy anyway. Does it give you an idea of visually what a derivative now looks like, right? On a space curve, a derivative is just the direction of the curve at that point, and the length of that vector would be the velocity that we're traveling. And that's exactly what space curves tell you. R dashed of t is the velocity vector. So if you've got an object and it's moving along a spiral, an aircraft doing its thing, and you find the derivative at any given value t, you're finding the velocity vector, right? So it's not 42 anymore, it's 3 numbers. A big vector is a big thing. So what is speed then in 3D? Speed is the magnitude of the velocity vector, right? Big long vector, you're going really fast. Very small, tiny little vector, you're crawling along at a very slow speed. So what does a second derivative get you? If a first derivative of a space curve gets you a velocity vector, what does the second derivative of a space curve get you?
Acceleration.
And you get the acceleration vector. Now, most objects that I know in the universe, at least, don't they travel in 3D, at least 3D, right? 3 dimensions. So can you see this is a much more realistic way of describing the motion of an object in 3 dimensions? You really need a space curve in 3 dimensions, right? And so its velocity r dashed is, you know, this guy. Second derivative is this guy. And so we talk about velocity vectors now and acceleration vectors, right? So it's not a single number like 42 anymore. It's a vector, a 3-dimensional vector. Now, almost everything we're going to do with these space curves is going to be connected to derivatives. But for completeness sake, we should integrate one, shouldn't we? Must be possible. So here is the notation. And you're going to do it from, say, 0 to 1. And so I want you to imagine that I have a space curve. And at t equals 0, it's here. And at t equals 1, it's here. And put my little x, y, and z values on it. and you'd like to integrate this fella. Let's make him this guy. So it's going to be t squared, 2e to the t, 5t, take away 1. Okay. If the world was nice again and everything was straightforward, how do you think you integrate a space curve?
Integrate each variable separately.
Yeah. So you find the integral from 0 to 1 of t squared, the integral from 0 to 1 of 2e to the t, and the integral from 0 to 1 of 5t take away 1. That gets you what? A third t cubed, so that gets you a third. That gets you 2e to the t, so it gets you 2e take away 2. And that gets you 5 halves t there. That gets you 5 halves t squared minus a t. So that gets you 5 halves, take away 1, 3 halves, okay. Do you see that the answer you get is again not a number, but it's a vector? So remember Calc 2, aren't integrations very closely related to the area under curves? Right, that's when it, the integral from 0 to 1 of x squared, right, is the area under x squared from 0 to 1, right? Can you see that that way of looking at integrals doesn't work anymore, right? That's not a number, that's a vector. So you might be thinking, what the heck is it then? Right, I've got the thing, but what is it telling me? Anyone want to tell me what they think it's telling me before I tell you what it's telling you? Because you might have a good intuition into this.
Is the magnitude the volume under the curve?
Oh, that'd be a cool thing. No, but I like your thinking. And the other ideas, what on earth could it be? Okay, here. It was certainly asking too much for you to just do it, because you've not really seen these in your life before. But it's connected to, well, let me have to do a side issue before I explain it, because it's a little bit messy. Can you remember doing a formula that looks like this from Calc 2? You remember that guy? It's the average value of the function, right? So if you imagine a function that went like this from A to B, this thing here would tell you the average temperature, right? The average height, right? It would be a number somewhere about here, right? It's essentially the average value, right? Okay. This integral here is the average direction that this curve is pointing at. Now, what on earth do I mean by that? Can you imagine at this point, it's pointing that way, and 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 this point is, and so on and so forth. You imagine that every single point isn't the curve pointing somewhere in 3D space. Can you imagine averaging out all those directions? And so what you're getting is the average direction that that curve is traveling from start to finish. Right? The average direction of the curve, right? So if the curve points down a lot, wouldn't it be that way, right? The curve is, and it's in 3D, right? So how could that be helpful? Can you imagine you've got a jet that's flying to bomb someplace, and you would like to know where it's flying, but jets don't typically travel in straight lines. Don't they just turn and twist all the time? If you found its average value, wouldn't you know where it was heading? even though at any point in time it might be curved and pointing somewhere else, its general direction is northwest or whatever. And then you'd say, northwest is insert name of city here. Matthew, you get your hand up.
Yes, would that be for the integration of the derivative?
You mean because I'm talking about the
Yeah,
point in the direction?
because that's essentially just
Yeah.
taking the end point and then subtracting the first point, which is just the same as integrating the derivative.
It is connected to the derivative. Yes, it's like adding up a whole load of derivatives.
And because you said that it's the average value, it would just be the average position, not the average slope, I don't think.
I'd have to think of that. It might, well, if you think of position vector as being the coordinates, then yes. I agree with you.
Okay.
When we talk about a point, like this point here, in the space curve world is a vector.
Yeah.
Right. And then a position vector just tells you its location. So if you're thinking it in that way, I would agree with you. Yes.
Okay.
There's not an awful lot of demand for integrals, so we don't do them much, right? But for completeness sake, I thought I would add that in. Do you all like the analogy of crashing to your death on the roller coaster? Okay. I think this is a really cool place to finish. So has anybody got a joke for me while you're all putting your last names down? I could do a joke to finish this week.
Yeah, I've got one.
Oh, good. What you got?
What is the most useful letter to a deaf woman?
This is going to be suitable, right?
Huh?
This joke is going to be suitable.
It's gonna be what?
Suitable. Could you tell your grandmother it and she would not be offended?
Oh yeah.
Okay,
Suitable.
we're good.
Sorry, I heard syllable. And I was like, no, it's a letter.
Okay, I've kind of wasted your joke, so we'll start from the beginning, right? Do your joke as if I'd be just starting.
Okay, what is the most useful letter to a deaf woman?
I don't know. What is the most useful letter?
The letter A. It makes her hear. It makes her
Oh,
when you add the
God,
letter A.
spelling. Oh, God. Okay. Did you hear about the dyslexic, agnostic, insomniac? They stayed up all night wondering if there was a dog.
Oh, that's a good one.
No, that's all I got for you guys. Have a nice weekend. I'll see you on Monday.
Thank you.
You have a good weekend.
You too, guys. Bye-bye. Okay, who's got the questions? David, you got a question?
Just curious, how many test questions do you think you're gonna do about?
No idea. I couldn't even guess. I haven't even looked at it yet. I'm going to start looking at it as soon as we leave and make one up. But until then, I don't know. It's the usual thing. They should take 90 minutes. I'm trying to, off the top of my head, think of how long are the questions in homework? That's always a good idea. A typical homework question. What does it take you? Are they all over the place? Some are really long and some are short.
Yeah,
Yeah.
I mean, just speaking for myself, I'm still on the first problem set. So
Right. So if they're going to be long questions, then you won't get many for that reason. I mean, if I was doing space curves, for instance, wouldn't those be very quick? You could do a derivative really fast. But you know, some like trying to find the equation of a plane when you're told the coordinates are 3 points, that question take forever, right? Because there's so much to it. Right. So there's always going to be about 5 questions anyway, because you know there's got to do a couple of questions per section. So if most of them are long, like you're saying, then it won't be much more than that. Any other questions?
Yeah.
Yes,
So
Dylan.
I have a question on what we just did.
Sure.
When you were taking the integrals
Mm-hmm.
from 1 to 0, I think that you just did the integral and then did all of the math for 1 to 0
Yeah.
and then wrote it down.
Correct.
But I don't quite
No,
know
I may
how
have
you
done
got-
one of them wrong. So which one are you uncomfortable with the answer because you
Oh.
didn't get the same as me?
It would be the last one,
This one here. Okay,
the
so
3 seconds.
so it's 5/2 t squared, take away t, evaluated at 0 and 1. So 5/2 times 1 squared, take away 1, minus a whole load of nothings. So 5/2 take away 1, 3/2.
But where did you get the 5/2?
Add 1 to the power, divide by the new power.
That was my mistake. Okay. Thank you.
Okay,
And then I have one more quick question if you have a moment.
sure.
It's on the first problem set. It's, I believe, question 7.
Let me go hunting for it. So what section are we talking about? 12.
12.4.
12.4 cross product. Gotcha. And
Yeah, I don't have 7 through, I think it's 9 or 10, because I'm not 100% sure what they're asking for.
okay, let's see what 7's looking for. So find a cross. Oh, so they're using the IJKs. Okay, let me show you. IJK are very special vectors. I is, oh, let me return to, I closed too many windows. Give me a second. Got my window back. Right.
No problem.
So I is basically that guy. J is that guy. And K is that guy. And they're saying, look, don't do cross products. Use the properties of I, J, and K. So for instance, if you take I and you do a cross product with J, you end up getting K. So if you do a cross product, right, with 2 of them, you always get the 3rd one, right? But sometimes the answer is negative. Give you an example. If I switch the order, you'd still get K, but you'd get negative K. So there's a little triangle that you can use that kind of helps you to do it. So I put a little I here, put a little J here, and I put a little K here, and I draw my little arrows, right? So the first question was I cross J cross K. Now, if you do I and J, you get positive K. So you get K cross K. So far, so good.
Yep.
Now, if you take a cross product of a vector and another one that's parallel to it, you always get the answer 0. So the answer to this one would be 0 vector. So if you did I cross I, you would get the 0 vector. If you do J cross J, you get 0 vector. You might say, well, why do you get the 0 vector? Cross products of 2 vectors that are parallel always get you the 0 vector. Now, the second one was K cross I, take away HI. So that became K cross I, take away 8 K cross J. You see, I'm basically distributing the K, just like a multiplication might be. Now, K cross I, there's K and I. So you're following the right. If you go with the arrows, the answer you get is positive. If you went against the arrows, like I cross K, if you went against the arrow, you get a negative answer. If you go with the arrow, you get a positive. So K and I get me a positive J. K and J get me a negative, right? Against the arrow, get me a negative I. And that becomes a J plus an AI. And then the last one is this guy cross product with this guy. Think of foil. Make sure I get my J's more J-like. You're going to get a J cross K, take away a J cross I, take away a K cross K, two negatives make a plus a K cross I. And then I just use my little triangle to figure out what this guy is. That guy is going to be some version of I, right? When you do a cross product of any two, the answer is the third one. So there's J and there's K, right? J cross K. I'm going with the arrow, so it's positive I. Take away, J cross I. J cross I. Would you agree I'm going against the arrow this time? Right? J first, I second, against
Yep.
the arrow. So that is a negative K. K cross K is 0, right? So 0 vector. And K cross J. K cross J. K cross J. Yeah, I'm going against the arrow. What do I get? I get negative I. And so what do I have here? I have an I, a plus a K, take away a nothing, take away an I. And oh, they cancel out. That's already 0. So all I'm left with is a K. And
That's pretty
the-
cool.
Yeah.
That helps a lot. Thank you very much.
Okay.
Have a great weekend.
You too. Maggie, you get any questions for me?
Yeah, I do.
Okay, what's your question?
Okay, so going back to Dylan's first question, can you explain that to me? How we went from all of the integrals to the numbers?
Oh, that part, yes. Okay. Okay. Yes, when I find the piece of, there we go. I couldn't find the right piece of paper. Here we go. So what we had was the integral from 0 to 1 of t squared dt. And that becomes 1/3 t cubed evaluated from 0 to 1. And that gets me 1/3 times 1 cubed, take away nothing, and that gets me 1/3. So that's the first one done. The second one was the integral from 0 to 1 of 2e to the t. Integrate that, you get 2e to the t, evaluated at t equals 0 and t equals 1. That gets me 2e to the 1, take away 2e to the nothing. So that's 2e take away 2. That's where that came from. And then the final one was the integral from 0 to 1 of 5t take away 1. And that guy becomes 5/2 t squared take away t evaluated at 0 and 1. That becomes 5/2 times 1 squared take away 1 minus a whole load of zeros. And that take away that leaves me with 3/2.
Okay, that makes sense. And then, so what is the notation for that? Is that the r-t dt?
This would be written down originally like that. And the answer, which we just found, would be that.
Okay. Sorry, I totally was confused on that one.
But you're not now, so that's good,
No,
right?
I'm not now. Right. So I had one more question, and it's also just the notation. So
Mhm.
when you were showing us from 13.1, I believe, number 10, or yeah, similar to number 10, you had the vector r of t equals 5/2, 0, 25/4. Would that be, would you write it the way, would you write it with
So-
soft parentheses, I guess is my question.
Okay, so here we go. So we had this guy. So those are always the parentheses that you use when your answer is a vector, right?
Right.
So I'm not quite sure what that question looked like again. So what did it start life off as?
So it's, sorry, go ahead.
No, what were you saying?
So you had t, 0, 5t minus t squared. But I guess I was just asking because you got, for one of the vectors, you had 0, 0, 0, and then you just wrote it as the point 0, 0.
Right.
Would we be expected to find the point, a point of the vector 5/2, 0, 25/4?
Now I'm lost. Right. So this is question 10.
Yeah.
Right. Let me find question 10 so I can get my head around what the darn thing was about. Okay. So question 10 was asking us for the coordinates of something, right?
I believe so.
Right. So we went and found out, for instance, that t equals 0 was one of them, and the other one was t equals 5/2, right?
Right.
Now, when you plug t equals 0 into a space curve, you get what's called a position vector. That's its name, right?
Right.
And a position vector can be interpreted as a coordinate. So when they ask you to find the coordinates of someone, you would write down this.
Okay.
So when you use a position vector at any given value, like in this case it would be at 0, the position vector is equivalent to the coordinates of the point.
Okay.
Right? So when I did this fella here at 5/2, I got a position vector 5/2, 0, and I can't remember what that one is, but it was something like
25/4.
25, yeah, 25/4. Now, that's the position vector of the point of intersection. The coordinates of it are simply just the same numbers again.
Okay.
And the reason you get away with this is the space curve gives you the position vector of any point. And so a position vector and a coordinate are very closely tied together. But when it's a coordinate, you use the curve brackets. And if they ever did say, give me the position vector, you would do that. But almost always they don't ask you for the position vector. They ask you for the coordinates of that point instead. So the notation is curved, coordinates, pointy guys, vector.
Okay, thank you. Yeah, that answers my question perfectly. I just wasn't asking it right.
Okay, I got you. Right, have fun then, and I will see you. I will see you later.
Yep.
Monday.
Thank you.
Or I
Thank
might
you.
see you June officer. That's also possible. Okay, bye-bye for now. I'm going to try and see if I can get some of those tests made up.